conditions. So let me touch on the difference between Venus and Earth and Mars, for example. So what am I showing here is A is Venus and B is Earth. So if you just look at the distance of Venus from the sun and Earth from the sun, the difference in temperature, Venus is almost 460 degrees near the surface, and Earth is a balmy 15 degrees on average. This difference cannot be explained by just the amount of energy being received from the sun. You need the greenhouse effect. So the Venus has what is called a runaway warming effect. It has created such a strong feedback within its system that it has created a very, very, very powerful greenhouse effect, leading to 460 degrees at the surface and 285 degrees of greenhouse effect. Whereas Earth has only a 33 degrees centigrade greenhouse effect, giving us a temperature of 15 degrees at the surface. Okay. Why did we care about this? Basically, because we want to know if we keep adding CO2 to the atmosphere on Earth, can we create a runaway warming effect or a runaway cooling effect? Like Mars has a runaway cooling, so its surface temperatures are minus 50 degrees. Can we create a runaway cooling or warming on Earth? This is why we looked at this so-called paleoclimate. Has there ever been a time in the past where the Earth has cooled so much or warmed so much? It turns out that there are times in the past where almost the entire Earth was covered in ice, call it snowball Earth. I won't go into too many details, but it is possible to take out CO2 so much from the Earth's atmosphere that you can create global cooling. So ice can come almost all the way down to the equator. And there have been what are called hot houses before, like during the Cretaceous or during the time of the dinosaurs, when so much CO2 was put in the atmosphere, more than 3 times what we have now, that all the ice everywhere had melted. Arctic had no ice, Antarctica had no glaciers. The Siberia was a lush green forest. There were dinosaurs wandering around all the way to the Arctic, and Siberia was full of mammoths and saber-toothed tigers and so on. So we have had very warm temperatures and very cold temperatures on Earth before. So we need to know what are the feedbacks that will kick in if we continue to emit carbon dioxide into the system. That's the whole idea of understanding past climates. Okay. Excuse me. So I will add a little bit to how the orbital forcing happens. So if climate has changed in the past, then what caused that? Obviously, human beings were not around during the time of the dinosaurs. So what caused it? We know enough about the solar dynamics now that we know how the Earth's tilt or the obliquity changes. Right now, it's about 23.4 degrees to the orbital plane on the sun, as shown here. That tilt changes from 22.5 to 24.5 on a time scale of about 41,000 years. We know this from the physics of how the planetary rotation works. And the ellipticity of the orbit, or the distance from the sun, the circularity of the orbit, right now the orbit is elliptical. The ellipticity of the orbit itself changes by about 0.2%, 2% on a time scale of 100,000 to 400,000 years. And Earth wobbles like a top. I think this animation, unfortunately, is not working here. But Naomi has the PowerPoint slides she can share with the participants. So because of the gravitational pull of other planets, the solstices and the equinoxes that we have now, we have a northern autumnal equinox on 21st September and the northern spring equinox on 21st March and the solstices on 21st December, 21st June. These themselves get pulled around by the gravitational pull of the Venus, Jupiter and Saturn and so on. So if we don't adjust the calendar, when the equinox and solstice will happen will keep changing on something like 21,000 year time scale. Okay, so these are very precisely calculable. We can use mathematics to calculate precisely when these changes will happen. So we know how orbital changes will influence the energy budget of the Earth in the next 100,000 years, for example. So that is also something. So in the past, we call it natural variability, which means these orbital changes at various time scales combined to change the energy distribution on Earth's surface. Hence, they either initiated an ice age or they terminated an ice age. And that is important because we want to understand right now whether we are initiating an ice age or terminating an ice age. And we will see that there is a very critical feedback in the system where initiating an ice age takes a long time, but terminating an ice age can be very abrupt. I think you know where I'm going with that, because if you think about the glaciers melting on Greenland and Antarctica, Arctica is disappearing and so on, they are going pretty fast. So the melting phase can go very, very fast, and the buildup will go very, very slow. So if we are in a melting phase, we have to be careful, mostly because the melting of Greenland itself will raise the sea level by about 60 meters, because that's how much water is locked up in the glaciers over Greenland. If you melt Antarctica, it will raise it by another 200 meters. So there's a total of almost 300 meters of sea level locked up on land in glaciers. Okay. Do people know what a glacier is? Naomi, can people answer whether they know what a glacier is?
Either via chat or you can unmute and answer. Anyone, I mean, I think everyone's quite clear on what a glacier is.
Okay, so Megan McClellan says she knows, so everybody probably knows. Okay.
Yes.
Yes, okay. So everybody knows. Okay, so to kind of bring that point around, climate has always changed, and what is different now? So if you look at one of the earlier figures I showed about paleoclimate here, it shows that the polar ocean was warmer by 12 degrees on the left side here during the Eocene, Paleocene time. That's PETM is Paleocene, Eocene thermal maximum, when a huge burst of warming happened, and we know that the global warming is actually happening much faster than that. So let's say your kid asks you, if the Earth has been so much warmer than before than now, so you can see that there's been a constant cooling over the last 50 million years to the present. So why are we worried about global warming if Earth has been so much warmer before? The point is that, yes, Earth has gotten warm and cold before, but we have not been around for that long. Modern human being has only been around essentially in the last 10,000 years in such large numbers with agricultural way of life. Before that, hunter-gatherers and Neanderthals and our ancestors like Kenyanthropus, Australopithecus, Ardipithecus, Homo habilis erectus, everybody has been there in the last few million years. So it's not that Earth will go anywhere or life will go anywhere. The question is, what will happen to us, right? We are not used to large changes in climate. So everything is about us. Can we survive? So climate has changed in the past, and it has changed because of natural changes in orbital parameters and sun's energy and internal feedbacks. But now we are tinkering with a system on a large scale by converting carbon that's buried inside the earth and putting it in the atmosphere. So life has critically depended on changing climate, and life has changed climate itself. So if you go back 540 million years ago, before we had trees, the trees only evolved around what are called Ordovician, Silurian, and Devonian, which in fact uh, the amount of oxygen in the atmosphere was not as high as at present till about 2 billion years ago. Slowly it started to increase, and when photosynthesis became very abundant, then the oxygen increased in the atmosphere. When oxygen increased, the size of the life increased, and they adjusted and became, for example, a dragonfly of 2 feet wingspan could be found if you go 540 million years ago. But it became clumsy to fly around to avoid predators, so it got smaller. Fish have evolved, and so on and so forth. And when trees, in fact, evolved in very large numbers, they sucked down so much carbon dioxide, they created a global glaciation, which buried a lot of the photosynthetic material or hydrocarbon that they had produced. So this period called Carboniferous, here, I don't know if I don't have a pointer, but uh, the Mississippian and Pennsylvanian around 360 million years ago. It's called Carboniferous because that's where almost all of the coal we have now got generated, because the photosynthesized material got buried deep inside and got converted to coal. So that changed climate in a major way, and so on. So climate has been part of the evolution of life. So it's not necessarily a bad thing. And I will show in a minute that our own evolution probably depended on a critical climate change that happened around 2 to 3 million years ago over East Africa. So here is an example of land distribution around 120 million years ago. And you can see that India is sitting way south near Madagascar, Australia is way south near the pole, and so on. And again, you can see that the connection between the Pacific, what we call currently as the Pacific and Indian Oceans, is very different. The connection between the Mediterranean and the Indian Ocean is very different. Connection between the Atlantic and Pacific is very different, and so on. And there are ways in which we construct these locations in the past using magnetism and so on. So you have to basically figure out the time when India was there and its location. So you will need two clues. One is where was it and when was it. So that's how we do it. And using current climate models, we can easily put the continents wherever we want, and we can create past climates. So we can look at how the ocean circulation will be different, how the glaciers will be different, how the ocean, the atmosphere, where it will rain, and so on. And these light blue areas near the continents are what are called shelf areas, where the waters are very shallow. Those are very critical because that's where sunlight and the amount of nutrients that are available can change the evolution of life. For example, they can allow phytoplankton that would have been predominantly in the ocean to colonize land and then begin to grow into trees and so on and so forth, or for some reptiles to get on land and eventually evolve into something else. Okay, so let me try to slowly move towards some of the issues of climate change coming into the current era. So main message was, in the past, climate has changed because of sun's energy, continental distribution, but CO2 has always been a major player in the feedbacks that are involved in cooling or warming. That's something important to remember. So if we look here on the left, global fossil CO2 emissions from 1990 to about 2019. Obviously, we are increasing the amount of CO2 we are putting in the atmosphere and the rate at which we are putting it in the atmosphere. So during the decades of the 90s, it was increasing about 1% per year and then about 3% per year. And 2010 to 18, because of financial markets down, this, that, and so on, efficiency increase or whatever else, the rate had decreased, but more recent data shows that we are increasing again. Okay. So the amount of carbon in the atmosphere can be measured very precisely and very accurately because it is a gas that is very well mixed by the winds. It's very inert. It's circulated and mixed up. So if you measure it in Hawaii, it will give you a good sense of how the whole northern hemisphere. If you measure it in some southern hemisphere location, it will give you a good sense of what is the CO2 level in the whole of southern hemisphere. There is a slight difference in the southern and northern hemisphere because air cannot move easily across the equator and so on. But CO2 can be very easily and precisely measured and accurately measured. What about temperature? So that is where most of the debates about climate change have been brought in by the energy companies and people who don't understand or don't want to understand how climate change works. So here is a plot I'm showing of global temperature and carbon dioxide going back to about the beginning of industrial revolution. Even though industrial revolution started earlier, we consider 1850 as the beginning of the industrial revolution because that's where we get temperature data back to. It's harder to get reliable temperature past 1850 without reconstructing it and so on. Nonetheless, you can see the red line, which is showing the temperature, and carbon dioxide, which is shown in the yellow line. Carbon dioxide is increasing almost monotonically, has gone from about 290 parts per million by volume, which means if you take 1 meter cube of air in the atmosphere, there is about 310 parts of it are carbon dioxide, so very tiny amount. It's called a trace gas. And the temperature is not going up and down smoothly. This causes a lot of confusion, and a lot of confusion is created systematically by interests other than, whatever. So why does this happen? Essentially, the system, Earth system, which I will define in a minute, is able to hide away carbon dioxide and change the temperature non-monotonically. So we know carbon dioxide being put in the air because we know how much fossil fuel we are burning. It's a very cash crop, so we are tracking it very carefully since the time of coal and natural gas and oil and whatever else. So we know how, and we can measure it in the atmosphere. But carbon dioxide can go into the ocean, can be taken up by the peatlands, wetlands, salt marshes, forests, and so on and so forth, right? Soil. So the temperature need not increase monotonically. It goes up and down, and imagine the ocean. I think I can ask another question, even though people are not able to pipe in. Which one can hold more heat, ocean or atmosphere? Obviously, it's the ocean because it's like that pot and the fire I showed before. If you put a pot on the fire and start warming it, with water inside. Water warms up slowly and cools down slowly, whereas the pot can warm up fast and cool down fast. It's related to what is called heat capacity. So heat capacity of the atmosphere and land are very small compared to the ocean, and the ocean is deep, 3-4 kilometers. So 90% or more of the additional energy that we are trapping because of increased carbon dioxide, more than 90% of the additional energy trapped by the carbon dioxide is going into the ocean. And the ocean is circulating. So you might have heard things like El Nino and so on, which I won't go into unless somebody asks questions. So ocean can keep the heat for a long time. Sankalp, let me come back to you in a minute. You can ask it again. So ocean can keep the heat for years, decades, and centuries, and it can put it back out quickly. So this exchange of heat between the land, the atmosphere, and the ocean can create temporary warming and temporary cooling. But what you have to see is the temperature, global mean temperature being shown here is still increasing. So people show this carbon dioxide and the temperature and say, haha, see, they are not at all related to each other. So Sankalp, what is the question?
The question is that I've heard it mentioned, this was relating to your previous section where you were discussing the global effects of the Earth dealing with climate change as a whole. So I've heard it mentioned that there are certain areas which have been relatively less impacted by deforestation. And an example that is given is the Indian subcontinent. So they say that sometimes this may lead to more contrasting climate systems on the planet itself, which can lead to effects that are hard to predict, because this has not happened before, where the contrast between two regions on the planet increases. I'm not sure how true it is.
Yeah, two things. One, I don't know if I have a satellite map of the so-called greening of the Earth in the last couple of decades. So when you say India is not affected by deforestation, it is slightly misleading. Satellite data shows that the leaf area index of India and China have increased, and China almost 70% of the greening is because of reforestation and afforestation and prevented deforestation. Whereas India, the greening is 80% or 83% of it is because of agriculture. Okay, so that is one thing. And as for such a contrast not having happened in the past, I may have a plot later on, but I can share with Naomi later on. Sahara, just about 9,000 years to 6,000 years ago, monsoon was so different that Sahara was very green. So all the civilizations around that time had moved away from the Nile and colonized entire Sahara, Lake Chad, whatever else you can imagine. Around 6,000 years ago, climate changed again and the rainfall became less and Sahara became a desert again. So all the people moved back towards the Nile. So such contrasts have happened in the past. It's not new. And the models, good models, do take into account the distribution of vegetation, including agriculture, grasslands, different types of trees, and also add human activities like deforestation and urbanization and agricultural land conversion and so on. So we have some skill in looking at how the contrasting land use changes affect climate. Okay?
Right. Thank you.
Okay. So pretty much everything we are seeing now in terms of land use change has happened in a natural setting. So looking at this plot again, if temperatures go up and down and CO2 just goes up, then how can you look at it? So you can look at it this way. Here, the blue plus signs are showing the temperature going up and down, but the red blocks are showing the decadal anomaly. So if you average the decades of the 60s, the 70s, 80s, 90s, and so on, you can see that each decade has been warmer than the previous decade. So even though year-to-year variability happens, since about the 60s, each decade is getting warmer than the previous decade. So at this point, you have to decide for yourself how you think about climate change. Are you going to think that this is not a big deal, or you're going to think that it is a potential risk? Okay, so that is a big philosophical question there, because depending on how you perceive the risk, your action may depend on it, but it's never that simple. For example, if you have a kid, then you probably start worrying about college funds for the kid before even the child is born, before even you have proposed to your girlfriend or boyfriend has proposed to you. So that risk you can easily perceive and save for it, but hardly anybody can think of the environment in which the kid will grow up and be willing to pay a tax for saving that environment. So these future risks are perceived very differently depending on whether you can visualize it as affecting you directly or not. There is also a concept called global commons, which I won't go into. So to jump to how climate change has affected the Earth system so far, these are what were reported by the last IPCC report released in 2014. The next one will come out next year in 2021, is being furiously written up as we speak. I won't go into the details, but essentially it collects all the evidence we have, the data-based evidence we have, and puts them into different categories. You can see on the lower left corner where it is said confidence in attribution to climate change goes from very low, low, medium, high, and very high. And at the bottom, you see that the observed impacts are attributable to climate change. Remember what I said before about detection and attribution. Physical systems, biological systems, human managed systems, and so on. So physical systems include glaciers, snow, ice, rivers, coastal erosion, and sea level rise, and so on. Biological systems include terrestrial ecosystems, as Sankalp was saying, forests, wildfires. We had some really horrendous wildfire in Australia. Marine ecosystems, corals dying, fisheries disappearing, biodiversity decreasing. There are heat waves in the ocean now that we can measure and look at their impacts. And human managed systems like agricultural, food systems, livelihoods, health, COVID, for example, and how our economy works. Is it environmental friendly? What is its ecological footprint, and so on. So the main message here is that if you look around the world, including the oceans, every continent and every ocean is basically measurably affected with various levels of confidence that is attributable to climate change. So the climate change is already has manifest itself in changes in the physical system, biological system, and human managed system. The question, of course, going back to Sankalp's point is, how are the feedbacks able to amplify or damp it? For example, if there is large-scale deforestation over Amazonia or Central Africa or Borneo and Indonesia, conversion to palm oil and so on, how does it affect local climate and global climate? We can use the models and some past examples to show that when you do large-scale deforestation, you can actually exacerbate the changes in rainfall and make it harder for the forests to recover. And warm temperatures, Australia, for example, the wildfires started and became so widespread and devastated, I don't know, more than 1 billion lives of animals because of the warm temperatures, because the warm temperatures quickly dry up the soil and convert the forest into a fuel for the fire, for example. So the US, which used to have seasons of wildfires, now basically has wildfires throughout the year. Canada, which is so far north, also has wildfire seasons and so on. So wildfires are a natural phenomena. They may be started by lightning and so on, but human activities, warming, drying of the soil, etc., can make them much worse, and they can have a positive feedback. The Australian wildfire definitely created its own weather, its own heating and winds that basically accelerated the fire. So the main thing we are always looking for is those kind of feedbacks that are present in the system.